Welcome viewers. In this video we are going to continue our design of substation equipment foundation in Eurocode. This is stage 4 out of 7. In this we are going to do foundation bolt design. These are all the various stages to complete the design of substation equipment foundation in Eurocode. The first stage, overview of calculation. Second is foundation and soil parameter and loads and load combinations. Third one is a stability check. So these three parts we already completed in our previous video, and this is a fourth stage. So in this stage we are going to do foundation bolt design. Followed by that, fifth is a design of a bottom slab, sixth is a punching and one-way shear, seventh is a design of a pedestal. So these three we are going to look after next week. Now let me move on to that Excel calculation. So on the screen you can see that Excel sheet which we are using for the equipment foundation calculations. So far we have completed the three series up to this stability check. Now we are looking at the foundation bolt. So this foundation bolt, first we need to extract the load from the foundation loads sheet. So this maximum resultant shear HR is 5 kilonewton. So that is we have extracted from this table. Generally this foundation bolt we need to do the design calculation based upon the SLS load combination only, not the ULS, because this is even the design itself we used to consider a lot of the material partial safety factors reductions, and the SLS load is suitable for this anchor bolt calculations. If we are considering the ULS, then it will be a over design. So that first input as a resultant horizontal force we have extracted from the foundation load combinations for ULS sheets, and next one is a vertical force Vz we need to consider again from the maximum one. So here that 11 is the maximum one, and we are assuming the face to face distance or center to center distance of anchor bolt at 400 mm. So assume these are the circle is anchor bolt. So this should be in the base plate of the structure, and after this, so I am showing in the plan view. So this is on the pedestal. So entire arrangement should be seated on the pedestal or the column of the equipment foundation. So this distance between anchor bolt is a 400 we have assumed here in both the directions x and y, 400. So this is somewhat assumptions we are doing here. So this is required in order to calculate the vertical force to be applied on the each individual anchor bolt. So now we are going to take two cases instead of having the various load cases according to the load combinations we are having. There are 50 number of SLS load combinations. Anyway, this SCF may not be applicable in most of the foundations, but here we are just considering for the demonstration purpose. In most of the European standard they simply ignore this short circuit force as it is very short durations, less than or equal to 3 seconds only. So this can be ignored, but only for the demonstration purpose we are considering this. So here what we are going to do is a maximum moment on y and x we are going to separate as a two cases. So here if you are taking that moment in y directions, if you are considering, means it is taken from this my, which is stating that 20 kilonewton meter is the maximum one. So accordingly corresponding to the bending moment my mx we are having only 0. So you can see in this, so the 20 which is having mx as a 0, so it is extracting the values which is coming is 0 only, and vertical force due to the movement to y is nothing but we are dividing this movement by lever arm distance. The lever arm distance is nothing but half of the spacing between the anchor bolt. So we are getting vertical force due to movement y is 100 kilonewton. Similarly, like vertical force due to movement x also we need to calculate. In that x movement we need to add it. Accordingly, the lever arm distance in y directions to be considered. So total downward force by the moment, we need to add these two, which is 100 kilonewton. And we already know that tension at plinth T is the total load, vertical load minus the 11. 11 is the vertical load which is in a downward directions. We all know this because from the equipment foundation structure design we have considered the hollow profile. So based upon that, the total vertical load will be in a downward load only, downward directions. So the tension generally means it is a uplift or pull. So this pull can be reduced by the vertical load, total vertical load. So it is coming 89 kilonewton is the total tension load. And coming to the compression, it is we need to add for this compression because the compression means it is a downward force only. So this compression 100 is the compression due to the bending moment, because if you are going to draw a center line here and apply a moment in these directions, so the moment is going to activate in these directions. So if suppose the moment is in these directions, then two anchor bolt will have tension and other two opposite two anchor bolt will have compression. So this is a phenomena. So this T represent the tension, C represent the compression. So these two anchor bolt will subjected to tensions as it is going to rotate in these directions. So these two anchor bolt will induce tension forces as it is going to end this side. This movement is going to compress or suppress this right hand side anchor bolt. These two anchor bolt are subjected to compression. So that is what we are considering tension and compression in caused due to the movement. So that we are adding to the total vertical force from the structure means it is a total compression, and we are reducing that 11 kN from the total vertical force due to the movement means it is tensions. So net tensions we have calculated and gross compression we have calculated for case 1, that is maximum movement in y direction case. Similar like maximum movement in x direction also we need to consider. So for that also we are going to consider the mx of the SLS load combinations. So here you can see 8.5 is the maximum. Corresponding to that my is 6.5. So the 6.y is we have considered here corresponding to with by using the VLOOK formula, so that this value can be directly taken from the foundation loads. Similar way we are going to apply the same principle such we have calculated in case 1. So likewise this moment divided by the lever arm distance, that is half of the center to center distance, because the lever arm distance is only half of the distance we need to consider, because the first half will be subjected to tension and another half will be subjected to compression. So the spacing between the anchor bolt 400 mm means we need to consider only the half of the spacing between the anchor bolts, that is 200 mm. So similar like here also vertical force due to movement x and y are arrived here. So this we are summating. So for doing this summation we are getting 76 kilonewton. So again this same principle we are adding here. So the total vertical force from the pedestal is 11 kN downwards. So this downwards we are deducting from the moment tension which is coming due to the moment is 76. So deducting that it is coming 65. Again adding this we are getting the compression 87 kilonewton is a gross compression and 65 is a net tension occurred in the anchor bolt area. So now coming to the number of anchor bolt which we have considered 4 number of anchor bolt. So diameter we have assumed as a 20 mm. So the gross area of anchor bolt is by d square by area, it is coming 314.16 square mm. And the stress area of bolt we need to consider as per the supplier catalog, or in generally it will range from 75 to 85%. So we are having a table here where we can have that bolt diameter and the stress value here. So generally this will from the supplier catalog, or we can arrive by applying some 75% to 80% of the gross area of the bolt. So here these are listed according to the bolt diameter which is extracted from the supplier catalog, and accordingly the based upon the diameter it will directly pick this value from the table which is added in this table sheet. And grade of bolt, so we need to identify if suppose pre-manufactured by the supplier, there will be some special kind of grade is applicable, but if it is not generally, then we need to consider as per the bold standard grades like 4.6 to 10.9. 10.9 is most probably avoided, or because of this galvanization, hard dip galvanization is not possible with the high strength 10.9 grade, because the surface itself very smooth. When coming to that ultimate tensile strength of the bolt, how to arrive from the grade is, it is very simple. The first whole digit, that 8, we need to multiply it by 100. We will be getting the 100 megapascal as a ultimate tensile strength. So second one is this fraction zero point 0.8, we need to multiply it with this 800, then we can able to get the yield strength of the bolt. So that is what the grading system is adapted. So this 800, 8 into the whole number 8 into 800 is ultimate tensile strength of the bolt, and the fraction zero point 0.8 multiplied by the ultimate tensile strength is the yield strength of the bolt. So this is a general grading system of the bolt materials. And coming to the actual tension on each bolt, so we already arrived the tension on the bolts. So we are having two classes, two cases. Case 1 for maximum movement y cases, another case 2 is a maximum movement about x. So we are considering the maximum among that and divided it by 4. So we are getting 22.25 is our per bolt tensions. Similar like shear force, we already have that resultant shear force as 5 kilonewton, so that we are dividing it with 4 number of bolts, then we are getting 1.25 kilonewton. So this partial safety factor gamma 2 we need to consider as per the class 7.3.51.1 of EN 50341. So this code we need to refer in order to get the factors. So you can see in the right hand side that code 50341, which is a overhead electrical lines exceeding AC 45 kV. So generally for most of the equipment structure and the foundation design, we need to consider some of the factors from here, as those are related to the electromechanical loads. So here in this you can see under the notes 2, it is mentioned that resistant in the net section at the bolt holes for connections we need to consider 1.25. So this is what we have considered here in this. And coming to the tension capacity of the bolt and shear resistance of the bolt, we need to calculate as per the table 3.4 of EN 1993 part 1 section 8. So here you can see the right hand side. So this is a table of 3.4 which is to be referred for design resistance for every bolts in shear and tension. So here you can see that shear resistant, sorry, tension resistant, you can see here K2 FUB AS divided by gamma W2. So here K2 value is 0.63 for countersunk bolt, for otherwise 0.9. So for our case is 0.9, which is not a countersunk bolt. So we have considered 0.9, and FYB we already calculated here as a 640 megapascal, and the area we need to consider the stress area, which is 245 for 20 mm dia. So that we have considered here. And coming to the shear resistance, alpha V into FYB into A. A here is again the stress area we can consider, and alpha V. So you can see here in the table right side, alpha V FUB A divided by gamma M2 is mentioned here. So gamma M2 is already, it is 1.25, and alpha V they have defined here for class 4.6, 5.6 and 8.8 it should be 0.6, and the remaining classes it is 0.5. So this is applied with VLOOKUP and referring to the table with respect to the grade of material which we have assigned. So now we are having the values for alpha y FYB, which is a 640 megapascal, and A is a stress value we can consider as calculated here 245, and applying all this value we are getting 96.5 kN. And coming to this code referral for combined shear and tension, you can find out here FEED divided by FERD. So this same formula we are taking here. So whereas FEED is a actual shear force on anchor bolt, FERD is a shear resistant per plane, and actual tension per bolt is 22.25, that is divided by 1.4 times the resistant tension resistant or tension capacity of the bolt. So applying all the values in this equation, we are getting 0.21, which is less than 1, hence we can say it is safe. And next we need to do the check for bond length in tensions. So far up to this level we are stating that the diameter which we have provided is safe, but we need to find out how much length this anchor bolt should be go inside the concrete, so that we need to decide based upon the concrete bond strength. So now let me see how it is to be calculated, and for that we need to, already we have calculated the tensile load per bolt, which is 22.25 kilonewton. We need to find out the tensile strength of bolt in its cross sections. So we need to divide this 22.25, that is a tensile load per bolt, divided by the gross area of the bolt which we have considered for 20 mm is 314. So this is a design strength of bolt, that is actual tensile stress which is going to occur in the bolt, which will act as a pull out or pulling force in the concrete. So this will give you, with respect to the resistant capacity of the bond strength of the concrete, this will give you how much length minimum it is required to penetrate inside the concrete pedestal. So for that ultimate bond stress in concrete we need to calculate. So we already assumed this grade of concrete as C25/30 in our initial stage. So our characteristic concrete strength in cube is FCK is 25 megapascal. So for that, in the right hand side you can see these are the equations, FPN 2.25 neta 1 neta 2 into FCTD is the general formula to calculate in that. So we need to find out this class 8.4.2. So for that we need to refer page number 36 of EN 1992 part 1 section 1. So here in the page number 36 you can see here in the right hand side PDF file. FCTT is a design tensile strength of concrete. So this is the equation we need to consider FCTT. So before that 8.4.2 we need to refer. So this is a formula to find out the ultimate bond stress which is required to calculate the embedded length. So here this 2.25 neta 1 neta 2 FCTT. So this is the same formula we have considered here. And now we can go to page number 36 to find out the full explanation about what is FCTT. So this FCTT we need to calculate based upon this equation, which is given in page number 36. FCTT equal to alpha CT into FCTK 0.05 divided by gamma C. So this gamma C value we need to refer 2.4.24, which is in page number 26. So here you can see for concrete gamma C, for persistent and transient we can consider 1.5. Of course for SEF we can consider 1.2. For better we can consider 1.5, which is will give a optimistic solution or higher, more critical solution. So as per these equations, FCTD should be alpha CT into FCTK 0.05, that is 5% fractal concrete strength we need to consider, and gamma C we already just seen it is 1.5 as per table 2.2. So where to find out this alpha CT and FCTK 0.05, we will see that. So page number 36 will give you the equation to find out the FCTT. So here alpha CT, the value alpha CT for use in a country may be found in its national annexes. The recommended value is 1, so we can consider the recommended value instead of going to refer into the national annexes. So depends upon the national annexer code, we need to refer what is the exact factor for this alpha CT. And gamma C also we have find out as 1.5 meter, 1.5, and alpha CT is 1 we have considered, and FCTK, that is the fractile concrete strength for 5%, we need to consider from the table 3.1. So for that we need to refer page number 31. So you can see in the screen for various FCK value. FCK is a characteristic strength in a cylinder. So for our case is C25 or 30. C25 is a concrete characteristic strength. C25 means this. For cylinder it is 25 megapascal, and for cube it is 30. So that's why we used to mention C25 bar 30. And for 5% fractile concrete strength, for C25 it is 1.8. So 1.8 we have applied like VLOOKUP, and based upon the table which we are listed here, so FCTK will be taken from this table. So it means we already consider alpha CT as 1, and we just now we find out from the table 3.1 of EN 1992 part 1 section 1 as 1.8. So I am multiplying that to 1 into 1.8, that is alpha CT into FCTK 0.05 divided by gamma C, we already find out it is 1.5. So our FCTD value is 1.2. So that's what here mentioning as it is calculated 1.2. And coming to this equation, so neta 1 and neta 2 we need to find out what it is. So this is the only unknown value now. So for that we need to go again the page number 36. Page number 135. So here we can able to find out the neta information. So neta 1 equal to, so neta 1 equal to 1 when good conditions are obtained. So we assume that we are going with a good concrete, good quality of concrete, or in case if we feel that it is not in good quality, there may be some defect in this concrete, then we can consider 0.7 accordingly. And neta 2 explanation is given as neta 2 equal to 1 for diameter less than or equal to 32 mm. So our case, our diameter is 20 mm, the anchor bolt diameter. Then we can directly consider 1 for both the neta 1. So that's what we are considering here, neta 1 and neta 2 as 1. Anyway, we are applying these equations like here in the neta 2 calculation, they are given some 132 minus 5 divided by 100 equal to, so this equation is given, but our case it is less than 32 mm dia, so we can consider directly 1. So now the same FBD we can able to find out by multiplying 2.25 as given in the equation, and neta 1, neta 2, and FCTT is a 1.2 megapascal. So multiplying all these values in these equations, we are getting 2.7. So this 2.7 is calculated here. So this is the ultimate bond strength in concrete. Next one, we need to find out the basic angle length of bolt. So this equation IB required is the total embedded length or length inside the concrete pedestal of anchor bolt is required. So that we need to calculate based upon class 8.4.3. So for that we need to refer page number 136. So here you can see these equations. LB required equal to 5 by 4 into sigma ST divided by FBD. So we already know that 5 is a diameter 20 mm, and as per the equation 4 is come into the divide, and 70.8 is a sigma ST. Design strength of bolt we have calculated as a 70.82, and finally the unknown value is ultimate bond stress in concrete, which we already calculated as FPT 2.7. So applying these values in these equations, we are getting 131 mm. So we are just round out to 140 mm. So we have mentioned like 4 numbers of 20 mm anchor bolt is required with the minimum embedment length of 140 mm. So this embedment length is very important while doing design of anchor bolt design. So above the concrete or above the pedestal top level, it should extend around 120 mm. So in total, the length of the anchor bolt required is 270 mm. Out of that, 120 mm is exposed outside the concrete, and 140 mm is to be penetrated or embedded inside the concrete. So this is a summary of anchor bolt. So far we have checked all the parameters required for the foundation bolt or anchor bolt. So diameter we have checked, and the number of bolts also we have checked, and the grade which is suitable for that also we have checked. We can also alternatively check with the 5.6 grade. So it is coming 0.44 as a utilization. And the embedded length, however, it is not increased because it is not related to the grade of the anchor bolt. It is related to the grade of concrete. So anyhow, and also suppose in order to think about the optimizations, we can also reduce the diameter to 16 mm. So let me try what it will happen if it is a 16 mm. So in 16 mm means the embedded length we record is 170 mm, and total length of anchor bolt is 290, and the usage factor also is 45%. So this is all about foundation bolt calculations for substation equipment foundation design. Thank you. Look description for more related videos. Subscribe to this channel for more updates. Thank you.